Hey everyone, and welcome to our deep dives today. I know you're ready to learn about non-thermal emission in radio astronomy, and you've brought some super interesting lecture notes and slides with you from a university course.
It's a really cool topic.
Yeah, it really is. We're going to try to figure out what's going on with this special kind of emission and how it helps us see some of the most energetic objects in the universe, like exploding stars and pulsars and even black holes.
It's like we get to use a brand new kind of telescope.
Exactly. So the very first slide from this lecture jumps right into the big question, thermal versus non-thermal emission. It's a pretty fundamental comparison, don't you think?
Definitely. It's like the starting point to understanding why non-thermal emission is so unique.
Okay, so let's start with what we all know, like thermal emission. The notes describe it as radiation that comes from how hot an object is. We see it everywhere, right? The heat from a hot cup of coffee, the light from a bulb.
Yeah, exactly. And the hotter something gets, the more intense the radiation. And even the color of the light changes depending on the temperature. Remember those red-hot stove coils? That's thermal emission.
Right. The notes talk about Planck's law, which describes how temperature and the emitted radiation are connected. We probably don't need to get into all the math for this deep dive.
No need to get lost in equations. The main thing to remember is that thermal emission comes straight from the object's heat. It's like a fingerprint of its internal energy.
Gotcha. So then we have the other side, non-thermal emission. This is where things get a little weird. The notes say it's radiation that isn't mainly from how hot an object is. So what does that actually mean?
Well, it means the energy source isn't just the temperature. It's something much more dynamic, like charged particles that are being accelerated to super high speeds.
So instead of heat causing the emission, it's the movement of these particles.
Yes. Think of electrons, like being whipped around by strong magnetic fields, like they're surfing on cosmic waves. And this acceleration, well, that's what causes them to release energy as radiation.
Whoa, that's a crazy image, electrons surfing on magnetic fields.
Yeah.
Makes you wonder what kind of crazy environments would cause that to happen.
Right, and that's what's so cool about non-thermal emission. It's a way to see these super energetic and wild processes happening out there in space.
So the next slide goes into something called synchrotron radiation, which seems like a big deal in the world of non-thermal emission. The notes say it's produced by relativistic electrons spiraling in a magnetic field. What exactly does that mean?
Relativistic just means those electrons are moving ridiculously fast, like a good chunk of the speed of light. And when they move through a magnetic field, they feel this force that makes them spiral around the magnetic field lines.
So it's like their crazy speed combined with the magnetic field that creates this unique radiation.
Exactly. And the radiation they give off isn't just one wavelength either. It's this wide range, from radio waves to X-rays, depending on the energy of the electrons and how strong the magnetic field is.
That's wild. The notes even mention that synchrotron radiation is polarized. Does that give astronomers more clues about where it's coming from?
Yeah, for sure. Polarization is like the direction the light waves are vibrating. By looking at how synchrotron radiation is polarized, astronomers can understand more about the magnetic fields in the area where the radiation is coming from.
Wow, so there's extra information hidden in the light itself. Okay, the next slide is about a particular equation, Larmor's formula. I'm no math whiz, but is this something we need to understand in detail?
Don't worry, we won't be doing any equations. But Larmor's formula is important because it explains a basic rule. Anytime a charged particle accelerates, it releases energy as radiation.
So it's not just about how fast they're going, it's about any change in motion. Makes
Right.
sense. And Larmor's formula is the math behind it, showing how much energy gets released.
Exactly. The formula tells us how much power is in the radiation that comes from an accelerating charge, based on the charge of the particle, how much it's accelerating, and some constants of nature.
Okay, so even if we don't dive deep into the math, it's good to know that this formula is behind the whole idea of non-thermal emission. Now, the next slide moves to cosmic sources of non-thermal emission. Looks like we're about to go on a tour of some of the most powerful places in the universe.
Yeah, get ready for some mind-blowing stuff. We're going to be checking out supernova remnants, pulsars, and even active galactic nuclei.
Sounds awesome. Let's start with supernova remnants. The notes say they're what's left after huge stars explode. I can already picture this incredible cosmic fireworks show. What makes these remnants glow so brightly in non-thermal emission?
Supernova explosions are just incredibly powerful. They release tons of energy and make these expanding shock waves that can move thousands of kilometers per second. And these shock waves, they speed particles up to almost the speed of light.
So it's those super fast energized particles again. And I'm guessing they're spiraling in the magnetic fields from the explosion, and that's making the synchrotron radiation.
You got it. Supernova remnants are super bright in radio waves because of synchrotron radiation. By studying this radiation, astronomers can learn about how the explosion happened, the strength of the magnetic fields, and even what the stuff thrown out from the star is made of.
It's like cosmic detective work. Okay, let's move on to pulsars. I always thought those super fast-spinning neutron stars were cool. What makes them such strong sources of non-thermal emission?
Pulsars are super fascinating. They're incredibly dense, with a mass bigger than our sun crammed into a ball just a few miles across. And their magnetic fields are crazy strong, trillions of times stronger than Earth's.
Wow, that's insane. So I guess those crazy strong magnetic fields must be why they give off so much non-thermal emission.
Absolutely. When a pulsar spins, its magnetic field sweeps through space, and that accelerates charged particles to crazy high energies. These particles then shoot out beams of radiation, including radio waves, and they sweep past Earth like a lighthouse beacon because the pulsar is spinning. That's why we see them pulsing.
So it's the combination of their crazy spin and those super strong magnetic fields that turns pulsars into cosmic lighthouses. And finally, we've reached the most intense objects on our tour, active galactic nuclei, or AGN. These are powered by supermassive black holes, right? The ones at the centers of galaxies.
That's right. And they're not your average black holes either. They're millions or even billions of times heavier than our sun. As stuff falls into these black holes, it creates this swirling disk of material that heats up like crazy.
But the non-thermal emission from AGN is even more dramatic, right? It's not just the hot gas, it's something else entirely.
Right. AGN have these powerful jets of material that blast out from the poles of the disk, and they shoot across huge distances at nearly the speed of light. These jets are where particles get accelerated the most, and guess what? They make a ton of non-thermal synchrotron radiation.
So we keep seeing the same pattern. Intense magnetic fields, particles getting sped up to crazy speeds, and synchrotron radiation being the giveaway. It's amazing how these things happen on such a huge scale across so many different cosmic objects.
It really is. And that brings us to why studying non-thermal emissions is so important. What can we learn by watching this energetic dance of particles and magnetic fields across the universe?
Ooh, that sounds like a great question to start with when we get to part 2.
Yeah, it's like opening up a whole new way of seeing the universe.
I like that. It's like every time we look deeper into space, we find even more amazing things.
Oh.
Okay, so the next slide is called Importance of Non-Thermal Studies. It highlights 4 big reasons why astronomers get so excited about non-thermal emission. Let's go through them one by one.
Sounds good. The first one on the slide is probing energetic phenomena. It's like we have a special kind of X-ray vision that lets us see stuff that would normally be invisible.
Right. We can't always see what's going on in those extreme places directly, but non-thermal emission lets us see the energy being released.
Exactly. Like when we study the synchrotron radiation from supernova remnants, we can actually map the shock waves from the explosion and watch how they expand and interact with the stuff around them.
So it's not just a snapshot in time, it's a way to watch these events happen. That's
Yeah.
pretty incredible. Okay, the second point on the slide is estimating magnetic fields. This one's interesting to me because magnetic fields are invisible, right? So how can we study something we can't even see?
Well, that's the beauty of non-thermal emission. Turns out the way synchrotron radiation behaves is directly related to how strong the magnetic field is and what direction it's pointing in.
So by analyzing the radiation, astronomers can actually map out these invisible magnetic fields that are all over space. That's pretty amazing.
It is, and it's not just about mapping the fields themselves. It's about understanding how important they are in all these energetic processes. For instance, with pulsars, those super strong magnetic fields are what accelerate particles to those insane speeds, which ultimately makes those lighthouse-like beams of radiation that we can see.
It's like the magnetic fields are the conductors of this amazing cosmic orchestra. Okay, the third point is measuring particle energies. I'm guessing this goes back to those charged particles getting whipped around at super high speeds. How can we actually measure how much energy something so tiny has when it's moving so fast?
The answer is in the synchrotron radiation, again. The spectrum of the radiation, how its intensity changes with frequency, directly tells us about how much energy the particles giving off the radiation have.
So by analyzing that spectrum, Astronomers can figure out how much energy those speeding electrons and other charged particles have. It's like a cosmic speedometer.
That's a great way to think about it. And this information is super important for understanding how particles get sped up to such high energies in the first place.
It's crazy how much information is packed into this radiation. All right, the last point on the slide is understanding emission geometry. What does that even mean?
Emission geometry refers to the shape and structure of the areas where the non-thermal radiation is coming from.
Okay, so it's not just about knowing what's giving off the radiation, but also about how it's being emitted and where it's coming from.
Exactly. By looking at the polarization and the shape of the radiation, astronomers can build a 3D picture of these complex environments. For example, the shape and orientation of the jets coming from an AGN can tell us a lot about what's going on in the accretion disk and the magnetic fields around the black hole.
It's like putting together a giant cosmic jigsaw puzzle. I'm really starting to see why astronomers are so interested in non-thermal emission. It's not just about seeing pretty lights in the sky. It's a powerful tool for figuring out some of the biggest mysteries in the universe. So the next slide in this presentation is called Discussion Questions. It's probably a good time to pause and think about what we've learned so far.
I agree. It's always good to take a step back and consider what all this means in the bigger picture.
The first question on the slide is, how does looking at non-thermal emission give us a different perspective compared to just studying thermal emission? What do you think about that?
That's a really good question. You see, thermal emission tells us about an object's temperature and what it's made of, but non-thermal emission shows us the energetic stuff, like the role of magnetic fields and how particles are accelerated. It's like seeing the explosive side of the universe instead of just its steady glow.
It's like the difference between looking at a photograph and watching a crazy action movie. Thermal emission is the photo, and non-thermal emission is the movie, showing us all the wild stuff going on. Another question from the slide is, why are magnetic fields so crucial in creating this type of radiation? They seem super important in a lot of these processes.
You're right, magnetic fields are super important because they're what give those charged particles the push they need to get to those crazy speeds. Without magnetic fields, we wouldn't have synchrotron radiation, and we wouldn't learn so much about these extreme places.
So the magnetic fields are the stage, the charged particles are the dancers, and the synchrotron radiation is the music and the lights from their crazy performance. Next question. What makes synchrotron radiation such a powerful tool for astronomers? We've touched on this, but it's worth repeating.
Well, synchrotron radiation is powerful because it tells us so much. It tells us how strong magnetic fields are and what they look like, how much energy particles have, and even the shape of the areas where the radiation is coming from. It's a super versatile tool that lets us study some of the most extreme stuff happening in the universe.
It's like the Swiss Army knife for radio astronomers, giving them all these different ways to study these crazy events. Okay, last question from the slides. What's the most surprising thing you learned about these extreme environments, either from these lecture notes or from your own research? This one is more open-ended, so I'm really curious to hear what you think.
You know, what always blows my mind is just how incredibly powerful these events are. Supernova explosions that are brighter than entire galaxies, neutron stars with magnetic fields trillions of times stronger than Earth's, black holes eating up matter and launching jets that stretch for millions of light years. It's almost impossible to wrap your head around how big and powerful these things are, and yet we can study them and understand them thanks to non-thermal emission.
It really makes you think, right? The universe is such an amazing and vast place, and non-thermal emission is like this key that unlocks some of its biggest secrets. Okay, moving on, the next slide is a key concepts review, which is a good way to sum up the main points before we finish.
Yeah, it's a good way to make sure we remember the most important ideas.
All right, first point. Accelerated charges emit radiation. This seems like the basic idea behind everything we've been talking about.
Absolutely. It's like the foundation of everything we know about non-thermal emission. It doesn't matter if it's electrons spiraling around in a magnetic field or particles getting blasted by a shock wave. The basic idea is the same. When you accelerate a charge, it gives off radiation.
And it's Larmor's formula that gives us the math to explain that, right?
Exactly. It tells us exactly how the power of the emitted radiation depends on the charge and how much it's accelerating.
Second point. Synchrotron radiation is produced by relativistic charged particles moving in magnetic fields. We've talked about synchrotron radiation a lot, but it's obviously super important when we're talking about non-thermal emission.
For sure. It's how most of the non-thermal radiation is made in a lot of space environments. And like we've already talked about, it tells us a lot about those environments, like how strong the magnetic fields are and how much energy the particles have.
Last point on the review. Non-thermal emission has a characteristic power law spectrum. Can you break down what that means and why it matters?
So a power law spectrum means that as the frequency of the radiation goes up, its intensity goes down, following a specific mathematical pattern. This is different from thermal emission, which has a peak at a specific frequency that depends on temperature.
So just by looking at the shape of the spectrum, astronomers can tell if they're seeing thermal or non-thermal emission.
Exactly. The power law shape is dead giveaway that we're looking at radiation that's not just from heat.
That's super cool. It's like the radiation has a fingerprint that tells us where it came from. Well, it looks like we've covered a lot today, and this next steps slide makes it seem like we've only just started to learn about this incredible field.
There's always so much more to explore. The universe is this vast and exciting place, and there's always something new to learn.
I totally agree. This slide suggests going back over the lecture notes, taking a quiz to test our knowledge, and checking out some extra resources to learn even more. But before we wrap up this deep dive, I want to leave you with one last question to think about. Something that goes a bit beyond what we've talked about today.
Oh, I like that. Hit me with it.
So we've been focusing on how non-thermal emission helps us understand objects in our own galaxy. But what could we learn if we studied this kind of radiation coming from even farther away, like from distant galaxies?
That's a fantastic question. Who knows what incredible things we might find out there? The universe is full of surprises, and I'm sure non-thermal emission will keep revealing them as we keep exploring.
Couldn't have said it better myself. Thanks for joining us on this journey of discovery. You know, it's funny, isn't it? The more we learn about the universe, the more questions we seem to have. But that's what I love about it. It's always pushing us to explore further. What really gets me about non-thermal emission, it's like this idea that it's like a message from space, bringing us information about these crazy events that are happening billions of light years away. It's like we're listening in on the universe's most energetic conversations.
Yeah, that's a great way to think about it. When we study these signals, we're not just sitting back and watching, we're actively trying to figure out the messages that are hidden in the radiation.
Exactly. So this brings us to the very last slide in this lecture. It's called Suggested Next Steps. And it looks like the professor wanted to encourage students to keep learning about non-thermal emission.
It's a good reminder that learning never really stops, right? Especially in a field like astronomy where things are always changing.
Totally. So the first suggestion is pretty straightforward. Review the lecture notes. It might seem obvious, but sometimes going back and looking over the material again can really help things sink in and maybe even spark some new ideas.
It's like when you go back to a place you've been before and you suddenly notice things you didn't see the first time.
Yeah, I like that. Okay, second suggestion. Complete the quiz. Quizzes are a good way to see how much we've actually learned and maybe figure out where we need to study a bit more.
Plus, they can be kind of fun. It's always satisfying to see how much you know.
I agree. Okay, and the last suggestion is explore other resources. This is where things get really interesting. It's basically an invitation to go beyond the lecture and dig deeper into areas that really grab our attention.
There's so much amazing stuff out there. Textbooks, research papers, documentaries, even podcasts like this one.
Exactly. There's a whole world of knowledge out there, and it's constantly growing. There's no shortage of opportunities to keep learning and exploring. Well, I think we've got a pretty good job diving deep into non-thermal emission. We've covered the basics, taken a tour of some of the most extreme places in space, and seen how this special kind of radiation gives us this incredible window into the universe's most powerful processes.
And hopefully we've inspired you to keep learning more. Who knows what amazing discoveries are still out there waiting for us? The universe is full of surprises.
Couldn't have said it better myself. Thanks for joining us on this journey of discovery, and until next time, keep looking up.